Definite integral to find the area. Under a curve, you take a function like f of x equals x squared and divide the region into rectangles, then add up all their areas. So for the integral, you get rectangles with width delta x and height f of x, giving you the Riemann sum. But the more rectangles you use, the more accurate your answer. So we take the limit as delta x approaches 0. And our answer is, it turns out that the definite integral gives you the exact area under any curve between 2 points, using the fundamental theorem of calculus. Indefinite integral to find the antiderivative of a function, you simply reverse the process of differentiation. So if f of x equals 2x, then the indefinite integral is, where c is the constant of integration, because when you differentiate any constant, it becomes 0. But if the function is more complex we add 1 to the power and divide by the new power. So we get, it turns out that to find the indefinite integral of any polynomial function, you just add 1 to each power and divide by the new power. Improper integrals are what happen when you get a bit too ambitious with your limits. Sometimes you're integrating from negative infinity to positive infinity, or sometimes your function has a discontinuity right in the middle of where you're trying to integrate. Instead of giving up like a normal person, mathematicians decided to take limits again. So for integral, you replace infinity with some variable t, integrate normally to get, then take the limit as t approaches infinity to get 1. Sometimes these converge to a nice finite number, sometimes they blow up to infinity. Multiple integrals let you integrate over regions in higher dimensions. Instead of finding area under a curve, you're finding volume under a surface, or even higher dimensional quantities. A double integral gives you the volume under the surface, over some region in the xy plane. You evaluate it by integrating twice, first with respect to one variable while treating the other as constant, then with respect to the second variable. Triple integrals work the same way, but in 3 dimensions, giving you things like mass, charge distribution, or probability in 3D space. These are fundamental in engineering, physics, and statistics. Line integrals let you integrate along a curve instead of over an interval. Imagine you're walking along a winding mountain path and you want to calculate the total work done against gravity. That's a line integral. You take your function, multiply it by a tiny piece of the curve, and add up all those pieces along the entire path. So, where c is your curve and f is a vector field. This shows up everywhere in physics when you're calculating work, circulation, or flux. The key insight is that the path matters. Taking different routes between the same 2 points can give completely different answers unless you're dealing with conservative vector fields, but that's another story entirely. Surface integral. This is used to integrate over a 2-dimensional surface in 3-dimensional space. So instead of integrating along a curve, we're integrating over a surface where S is our surface and ds is a small piece of surface area. For example, if we want to find the flux of a vector field through a surface, we calculate where F is the vector field and n is the unit normal vector to the surface. Volume integrals are triple integrals that calculate quantities distributed throughout 3D regions, things like total mass, electric charge, or energy density. The notation means you're adding up the function f at every point inside the volume V. The tricky part is setting up the limits of integration correctly for your specific region. You might use Cartesian coordinates for boxes, cylindrical coordinates for cylinders, or spherical coordinates for spheres. Contour integral. So far, we've been dealing with functions that work on real numbers, but what about functions that work on complex numbers? We integrate along paths in the complex plane, using where c is a closed contour and z is a complex variable. This becomes incredibly powerful when combined with residue theory, because if f of z is analytic everywhere inside and on, then the integral equals 0. But if there are singularities inside, then we can use the residue theorem to evaluate the integral. Quantum integral, also called path integral. This sums over all possible paths. A particle can take between 2 points, using where is the action functional, and you integrate over all possible paths. Imagine a particle going from point A to point B. It doesn't just take one path. It takes every possible path simultaneously, and you add up all their contributions with different phases. This is the foundation of quantum field theory and explains why quantum mechanics is so weird. Stochastic integral. This is used when you need to integrate with respect to random processes like Brownian motion instead of regular variables. So you get where W of t is a Wiener process, which is basically mathematical white noise. But here's the problem. Brownian motion is nowhere differentiable, so you can't use normal calculus rules. Instead, you need Ito calculus, where even the chain rule gets extra correction terms because randomness doesn't behave like normal function. Functional integrals are integrals where the variable of integration is itself a function. Instead of integrating f of x, you're integrating. Where phi is an entire function and d phi is some mystical functional measure. Fractional integrals let you integrate a function halfway or any non-integer number of times using the Riemann-Liouville definition. If alpha equals 1, you get regular integration. If alpha equals 1 over 2, you get half integration, whatever that's supposed to mean. This connects to fractional calculus, which is useful for modeling systems with memory effects like viscoelastic materials. The Lebesgue integral is what happens when mathematicians get frustrated with Riemann integrals not working on sufficiently weird functions. Instead of dividing the x-axis into intervals, you divide the y-axis into intervals and ask, which x values give function values in this range?